Have you ever looked up at the night sky and seen the Aurora Borealis dancing in vibrant greens and purples? Those stunning displays are more than just a light show. They're a sign of something powerful happening in space. Geomagnetic storms. But what exactly are these storms, and could they affect something as deep and fundamental as Earth's core? Let's dive into the science behind geomagnetic storms, explore their effects on our planet, and find out if they can really reach the heart of Earth itself. To start, we need to understand what a geomagnetic storm is. Picture the sun as a colossal fiery dynamo constantly churning out energy and particles. Sometimes it unleashes massive bursts of plasma and magnetic fields called coronal mass ejections, or CMEs. When these CMEs slam into Earth's magnetic field, they can trigger geomagnetic storms. Disruptions in the magnetosphere, the invisible shield that protects our planet from solar radiation. These storms are like cosmic tempests, shaking up the delicate balance of Earth's magnetic environment. Now, Earth's magnetic field is generated deep within the planet, in its outer core, a churning, molten layer of iron and nickel about 2,900 kilometers beneath the surface. This liquid metal flows and swirls, driven by heat from the planet's formation and radioactive decay. The motion creates electric currents, which in turn produce the magnetic field that envelops Earth. This field is what deflects most of the solar wind, a stream of charged particles from the sun, and keeps our atmosphere intact. So when a geomagnetic storm hits, does it rattle this deep, dynamic core? Let's break it down. Geomagnetic storms primarily affect the magnetosphere, which extends tens of thousands of kilometers into space. When a CME collides with this field, it compresses and distorts it, injecting energy and particles into the upper atmosphere. This is what sparks auroras, as charged particles excite gases like nitrogen and oxygen, making them glow. But the effects don't stop there. These storms can induce electric currents in Earth's crust, known as geomagnetically induced currents, or GICs. These currents can disrupt power grids, pipelines, and even satellites. In 1989, a powerful geomagnetic storm caused a blackout in Quebec, leaving millions without power for hours. But what about the core? To figure out if geomagnetic storms impact it, we need to consider how deep their influence can reach. The Earth's crust and mantle, the layers above the core, are poor conductors of electricity compared to the outer core's molten metal. When a geomagnetic storm induces currents in the crust, those currents are relatively weak and confined to the upper layers. The mantle, which is mostly solid rock, acts as a barrier, insulating the core from these surface-level disturbances. The core itself is far too deep and shielded for these induced currents to have a significant effect. Still, could there be subtler, long-term impacts? Scientists have wondered if repeated geomagnetic storms might influence the core's magnetic field generation over geological timescales. The outer core's fluid motion is sensitive to external magnetic fields, but the storms we observe are fleeting, lasting hours or days at most. The core's dynamics, on the other hand, operate on scales of thousands to millions of years. Any external magnetic perturbation from a storm would be like a single ripple in an ocean. It's simply too small and short-lived to alter the core's massive churning system. Another angle to explore is the magnetic field itself. During a geomagnetic storm, the magnetosphere can weaken temporarily, allowing more solar particles to penetrate. Could this affect the core's magnetic output? Research suggests no. The core's magnetic field is incredibly stable compared to the fleeting chaos of a storm. Studies of paleomagnetism, Earth's ancient magnetic record preserved in rocks, show that the planet's magnetic field has persisted through countless solar events over billions of years. Even during extreme events like solar superstorms, the core's dynamo remains largely unaffected. That said, geomagnetic storms do have fascinating indirect effects. For instance, they can heat the upper atmosphere, causing it to expand. This increases drag on satellites, potentially altering their orbits. They also pose risks to astronauts, as increased radiation can penetrate spacecraft. On the ground, GICs can damage transformers, as seen in historical events like the 1859 Carrington event, the most intense geomagnetic storm on record. That storm caused telegraph systems to spark and fail, and auroras were visible as far south as the Caribbean. So, while geomagnetic storms wreak havoc in the atmosphere and on technology, their reach doesn't extend to Earth's core. The core is simply too deep, too insulated, and too robust to be swayed by these cosmic disturbances. But that doesn't make geomagnetic storms any less awe-inspiring. They remind us of our planet's place in the vast, dynamic solar system, where the sun's outbursts can light up our skies and challenge our infrastructure. As we look to the future, understanding geomagnetic storms becomes even more critical. With our growing reliance on technology, think satellites, GPS, and power grids, predicting and mitigating these storms is a priority. Space weather forecasting is improving, with satellites like NASA's Solar Dynamics Observatory keeping a close eye on the sun. By studying these events, we can better protect our world from their impacts, even if the core remains untouched. In the end, geomagnetic storms are a dazzling reminder of the sun's power and Earth's resilience. They light up our skies, test our technology, and spark curiosity about the universe. While they don't shake the heart of our planet, they do shake up our understanding of how connected we are to the cosmos. So, the next time you see an aurora, take a moment to marvel at the invisible forces at play, and rest easy knowing Earth's core is humming along undisturbed deep beneath your feet.